Yo. Okay, let's get started. Let me go ahead and start off by just posting the link to the stream on X. Nice. Very interesting. Okay. Yeah, my Wi-Fi is buns. Awesome, so that has been posted. Great. All right, I'm really excited. I'm gonna get some water, turn on the lights, and we'll go from there. Awesome. Okay. Alright, we are back, ready to tackle this. Awesome. Okay. Just gonna quit from some of these that we don't need. Awesome. Okay. So just for a little bit of a recap on where we left off on Monday, because Tuesday I got caught up in some work at my internship. So unfortunately, I wasn't able to do as much work as I wanted to on Next Voters. But anyways, we're back and we're here. So we left off by just understanding the high-level architecture that goes into the CompactPrompt pipeline or framework. And essentially, we learned that the CompactPrompt framework is used to basically compress the context that is associated to an agentic workflow. Now, this does not only include things like your prompts, but also external data attachments, and there's a variety of methods that it uses in order for that specific thing to happen, right? Specifically, in the design, right, in section 3 where we were talking about the design, let me just, yeah, there we go. So in section 3 where we're talking about the design, it specifically outlines exactly how it does this. There's a combination of hard prompt pruning, n-gram abbreviation, and numeric quantization. And we know these at like a high level. Basically the function of what they do, right? And how sort of how they approach it, but not exactly the low level implementation detail. That's stuff that we're tackling today, right? We know that hard prompt pruning is basically a way to score all the tokens within your prompt and then figure out low level tokens, or basically tokens that don't really meaningfully provide any information to a prompt, because that naturally happens when we're talking, right? So especially with like users prompts, that can happen. So it basically just goes through those prompts and finds those low level tokens, removes them, and then also has some sort of algorithm from the paper. It was talking about one from SciPy, where it's able to reconstruct a grammatically correct paragraph. Because when you remove some of these tokens, it might remove the grammatical integrity of your actual paragraph. So that all happens as well. Again, very high level, but this provides us with the foundation to really succeed today, right? Then we have n-gram abbreviation, which basically takes n consecutive words, right? So that just means maybe 2 words or 3 words or 4 words. And based off of the corpus of text provided, it's able to basically find all of these basically combinations of words, right? So you could have something like interest expense, which pops up like thousands of times within your Word document, or something like National Basketball Association, right? And when it sees all of these coming up together so many times, it will just abbreviate them into a human readable abbreviation. So, for example, in the case of like interest expense, it'll see that a lot of the times, and it'll just abbreviate it to IE. Or in the case of National Basketball Association, we all know, even in natural language, we call it NBA, right? So it will do these things automatically for us to reduce the amount of tokens that we have. And then we also have numeric quantization, which basically has essentially a huge number which maps to a specific number within a scalar factor that is like done by mathematical formula. And that way we're taking this huge number and we're basically reducing it to a counterpart which is lower in the actual number, right? So that means lower amount of tokens that are being used. But the issue is that when you do that, you lose some of the accuracy of that number, because now it's represented by another, like it's represented by a number, right? So by doing so, you're going to be reducing some of its numerical accuracy. And obviously this is user defined on based off of the actual outcome, or the context of which you're using the numeric quantization for. Like for example, in my case of political and civic, the civic space, it doesn't really need to be super duper accurate, because we're just doing general reportings for the regular user. But if we were doing something for like a government, for example, then it would change, right? Then we would need a very low amount of quantization to ensure a high level of accuracy. But that is not us. So again, that's part of engineering this. Anyways, that was a lot of the recap that we've done. And if I'm being totally candid here, I don't really understand numeric quantization to the level that I understand like n-gram abbreviation or hard prompt pruning. But that's why I'm doing this video, so that, or this live stream, I guess, so that we can go through all of this together. And once we understand this, we can actually create an implementation, hopefully. That is the hope later on in the near future, to the next voter's local agentic workflow. That way we're actually having a context engineering technique baked into the system to ensure not only better performance, but also very cheap infra costs. Because as we know from this actual paper, it talks about how from pre-existing literature, there's proof that models degrade in their performance, specifically their reasoning capability, when their context is bloated, right? But they also need enough context to allow for a complex reasoning to occur. So fine balance needs to be created, which happens through building this context management infra. So yeah, pretty cool stuff in my opinion. All right, so let's just continue on then, and let's actually learn this at a more deeper level and see how it will really help reduce the amount of context while keeping the semantic integrity, right? So that means keeping what we're trying to say, the meaning of our prompts and our information, while reducing the actual volume of what is said, right? In terms of like the natural language or the tokens being consumed. All right, so let's go ahead and do this. Hard prompt compression. So we're starting off with 3.1, and then within that, we're doing another subsection. Static self-information. We begin by constructing a large offline corpus comprising sources, consisting of Wikipedia, shared GPT conversations. Is shared GPT... Oh, wow, I did not know this was a thing. Oh, okay. So they deprecated the project. But that's basically probably what OpenAI does now by itself. So that's why you don't really need this anymore. And the articles like this, right, in RX, ARXIV. I'm curious, how do you pronounce this? I've never actually learned how to pronounce this. Oh, archive. Okay, so it's just archive. So, and archive articles. Then we compute unigram frequencies ft for every token t as shown below. So there's this like, there's some math involved. Don't be scared. We will ask ChatGPT to figure this out for us. But there is like going to be a little bit of a barrier because of the fact that I don't really know all of this, but that's why we go through all of this one by one. So anyways, in this is saying, then we compute unigram frequency. So let's see what that is. This is part of n-gram then, no? Okay, let's start off by just sending a screenshot off to Claude and asking for help, because it's a really good tutor in my opinion. Alright, so let's get that. And I'm just gonna go ahead and copy this. Come on, load. Thank you. And then I can just go here, paste this, and then I'm gonna ask it, what does it mean by unigram frequencies, and what does the mathematical model shown do to supplement the utility for unigram frequency. Okay. Alright, so I'm just gonna make this a bigger screen like that so that we can do this a little bit more better. Okay, unigram frequency is just how often a single token, a unigram, one word or subword unit, as opposed to bigram, which are pairs or trigrams, triples, etc., appears in a corpus. Corpus just means like a body of text, which I should actually ask. Does this just mean a body of text within the realm of AI? I'm pretty sure that it does, but you can never be too safe. Okay, so it's basically a body of text which is specifically made. I did not know that nuance. The more you learn. Okay, so let's go through this then. Unigram frequency is just how often. Okay, we read through that. It's the empirical probability of that token. If you grabbed a random token from the corpus, how likely is it to be T, which is just the token itself. Okay. So f of t is 1 over n, and then we're basically looping, I guess. This is sigma, we're looping through it. Does this just mean that we are looping towards all possibilities just in a mathematical motion? I see. Yeah, it's over. Yeah, we're just gonna have to go through it one by one to really understand this. You know what? There we go. And there we go. So perfect. So what exactly is going to talk about doing? Wait, why am I literally have the voice model that I can use. So I'm gonna do that from now on. So does it just convert it into a percentage of how much it occurs throughout the whole corpus text? Right, but that proportion can be multiplied by 100 to get that percentage. Right, but that proportion can be multiplied by 100 and that would be a valid percentage, correct? I love using these voice models because they just make things so much easier. Okay, great. All right. Sorry, my dad's testing the smoke alarms. Um, okay. Okay, so I actually want to do something here. Okay. So what exactly are self-attention? Self-attention. What am I saying? So what exactly is the static self-information and how does it help with the hard prompt compression? I see. So basically, the static self information through this mathematical model, which this is basically just a fancy for loop. That's like the easiest way I can explain it, right? What it does is this is your summation notation, which uses sigma, and it will basically loop through all of the tokens that you input in, and based off of that loop, it will so for each token that you put into this function, it will loop through the whole corpus body, and it will see if that specific instance of the token is equal to the token that you've inputted. And if it does, then it will increment by one. So that's what this is telling us over here, this part. And this is just telling us that we have to loop over all of the tokens, right, within the within the corpus text, and we're gonna basically then, through this notation, see whether it is equal to one another for each of the actual tokens within the loop themselves. Um, yeah. And then once we figure that out, we divide it by the total number of tokens, which is represented by n, and that gives us a proportion which can be converted into a percentage, and that's basically how often or how frequent that token is shown within the corpus. So in the case of this paper, they constructed a large corpus, right? So that's why they were talking about this, because this was the data that they applied into this mathematical model. Awesome. Okay. So I'm gonna just double check, make sure that what I said was right before I move forward. But we'll go from there. Hold on, I'll be back. Yeah, I'm back. All right. So let's continue here then. All right. Awesome, awesome, awesome. Based off of the progress that is happening currently, I want to get through hard prompt compression and textual n-gram abbreviation by today, and really just sort of internalize those ideas before I move forward with quantization. So that will be the goal that we've sought out for ourselves right now. So yeah, let's do it. Okay. What is static self-information? Okay. Based off of what you've told me and my own digestion of the information stood about the text itself, essentially, static self-information uses a corpus of text. In the case of the research paper, that was a offline set which comprises of sources like Wikipedia, shared GPT conversation, and archive articles. And what it does is it computes unigram frequency, which is essentially how frequent a token appears within the corpus of text, and it's modeled by a mathematical formula which uses a summation notation to essentially loop over every single token within the corpus and see if each token within that specific iteration is associated with an input token. And so we're essentially doing this for all of the tokens and seeing how often each token is being used within the corpus of text. And after that, we derive the actual score by using negative log 2 p of t, which I still have to learn. I want to understand what that means. But basically, before that, we first compute the unigram frequency, which I understand now. And then those frequencies are then further used within the actual self-information score, like the static self-information score. But essentially, at a high level, a static self-information score is basically a score which is assigned to each token, and that measures how informative that token is to that specific corpus of text. And there's two components that go into determining that score, and the first one, which I've nailed, is the unigram frequency, basically figuring out how frequent that specific token is within the corpus of text curated by you. And then after that, you use the self-attention score formula, which uses a negative log to actually fully get the final score. Okay. It's taking an awful lot of time. I guess that's what I pay for not using WhisperFlow. WhisperFlow would have done this faster, but okay, so it didn't even do it. Interesting. Great, so I have to say all of that again. Okay. So what exactly? Wow, that is creepy. They should not be doing that. Anyways, from my understanding of the article now, and also from my conversation with you, basically the static self-information is a way of assigning a score based off how informative a token is of text that you have curated, and the way that we determine that score is through two components. The first one is the unigram frequency, and the second one is using that unigram frequency within a new algorithm or a mathematical formula, which is the actual score itself. And the unigram frequency is essentially how frequent this token is being shown within the corpus of text, and it's modeled by the summation notation, which basically loops through all of the tokens within the corpus and sees if one token is associated to the actual target token, and if it is, we increment, and then we divide that by the total amount of tokens within the corpus, and that gives us a proportion which can be then converted into a percentage if we want to. But that proportion is basically how much that specific token is being seen within the whole corpus of the text. And the whole idea of static self-information compared to dynamic self-information, because both of them essentially do the same thing. They're both going to give us scores based off of the actual, they're going to give us scores to assess how informative a token is to a corpus of text. But static self-information does it in a way that is non-contextual. It does not look at the actual context surrounding that specific token, and instead uses purely deterministic ways, maybe you can think about it. So that's the nuance that I need to really capture right now. is what exactly is the difference between a static self-information compared to a dynamic self-information, because both of them will do the same thing. That they both serve the same function, which is to basically score how informative a specific token is compared to a corpus of text for an AI model, right? But what exactly would be the difference between static and dynamic? From a glance of, trying to understand this, I would think it would have to do with context, right? Static will not change the importance of a token based off of the position of which the token lives in and the surrounding context of it, but rather it's just fixed scores. Whereas in dynamic self information, it is based off of the position of the token and the surrounding text. Maybe that can happen through something like a self attention layer, or using an LLM, which I see now that we're using an LLM, which has that self attention layer, which can understand context. So that's probably what we're using there. But that's a really rough, if I'm being honest, that's a really rough understanding of the difference between static and dynamic, and that's purely intuition. So let's try to reason it out and make sure that it's good to go before I move forward. Please work. Let's go. Okay, awesome. That's a lot. I would not type that out, if I'm being honest with you. Okay, awesome. So, pretty much is right, I think, but there might be some rough edges, which I would assume. Okay, so what you got right. Static self-information assigns context-free scores. Yes, correct. The score for a token is a pure function of its corpus-wide frequency, nothing else. Dynamic self-information incorporates context via surrounding tokens. Correct in spirit. Okay, that's interesting. I don't know what exactly correct in spirit really means, but I guess we will learn that today together. Okay. LLMs with self-attentions are the mechanism for dynamic scoring. Correct. This is exactly how methods like selective context and LLM Lingua compute contextual self-information. They run the prompt through a small causal LLM, or LM, sorry, not LLM, it's causal LM, like GPT-2 or Llama 7 billion. Yeah, those are not really large models. And read off the per token probability the model assigns. Both serve the same function, scoring, importance, correct. Where your understanding needs tightening. Deterministic is the wrong word for static. You said static uses purely deterministic ways to construct it with dynamic. Both methods are deterministic in the computational sense. Run them twice on the same input and you get the same output. Okay, yeah. So, yeah, I guess I was just throwing around a buzzword, if I'm being honest. Yeah, that makes sense though. Deterministic is when you have a workflow or a piece of software which always produces the same output, given that you provided the same input over and over again. Whereas dynamic, or I guess non-deterministic workflows would be when a software system, given the same input, would give you a different output. And that would happen through LLMs. And I assume because dynamic has a backbone, its backbone is within an LLM, it would use that. Like it would have that sort of that same behavior, but apparently it doesn't. So, good to know. Okay, yeah. So it just clarified exactly where I was sort of still muddling. Uh, the real distinction isn't determinism versus randomness. It's context free versus context conditional. Static uses marginal probability. Dynamic uses conditional probability. And I guess marginal probability means it looks at the probability of a token or probability of any context without actually understanding the context that it lives in. So essentially, at a high level of just trying to digest what we've done so far. Static self-information, first of all, self-information itself, right, which is a component, sorry, that is what we're, okay, let me center myself here. Self-information is what is used by hard prompt compression to actually figure out what tokens should be removed. And essentially what it does is score tokens based off of how informative they are to the actual context, not context, but to the actual corpus of text that they're in, right? And it does that by, you could either use static self-information or dynamic self-information. So again, I will repeat this. Self-information is what powers the hard prompt compression. It essentially scores a token based off of a blob of text on how informative that token is to that specific text. And based off of that informative score, we can remove some of these tokens from the actual prompt, which reduces the overall size of that prompt, whilst also keeping semantical integrity, because we're removing low level or low impact tokens. We're not really removing stuff that would be actually important for that agent to do work. So that's where we strive that balance, right? That's where we're actually implementing that balance. Now there's two different approaches to self-information. First one, we have gotten, I would say 60 to 70% there, which is static self-information. This one is not context aware. That's the best way I can put it. It is not context aware. All of the scores will stay the same regardless of the surrounding tokens of the target token that you want to know its informative ability for, right? And this means that you will have lower accuracy because of the fact that there might be some times where a token might traditionally have been low level information, but in that case, because of the context or the words it's surrounded by, it's actually a very high level of importance. So it shouldn't really be removed. It's not worth it to remove it. But static self-information cannot actually grasp that. Dynamic self-information, on the other hand, can, because it's powered by LMs, right? Language models is powered by LMs, and these LMs have layers, self-attention layers, which are able to actually grasp context. So that is the real difference between static self-information and dynamic self-information. Okay, great. Now that I've digested this, again, I always follow an active reading approach where I read something and I spend like 10 minutes just trying to understand that really deeply. I think the ROI you get on just putting that time in is just unparalleled. So what I'm going to do now is I'll actually ask Claude, and I'm going to double check this because Claude did give me some very good feedback in the sense that, talking about determinism was wrong because both pipelines are deterministic, right? Because they will produce the same result regardless of any sort of constraint, just that obviously your input has to be the same. It's not like an LLM or like an AI chatbot where, if I put in the same prompt, if I put the same prompt in again, I'm going to get a completely different output, right? And that's because of the fact that within the layers of the LLM, they actually use some randomness in selecting the next token when they're computing for what the next most probable token should be. But anyways, that's not what we're talking about. We're talking about context management or engineering in agentic workflows. So let's stay on topic. Okay, cool. So now what I'm going to do is I'm actually going to take a little break because I have to use the washroom. But once I come back, I will work on just consolidating that information that I just learned. And then I will finish off static self-information by understanding this formula, which it takes the unigram frequencies that we now know how it works, and it uses that to actually find that self-information score. Because the unigram frequencies themselves, they are a proportion which could be thought of as a score, but they themselves are not a score. You actually need to take that frequency and put it into this function here to get a frequency, to get a score, which is meaningful in the sense that it will tell you how informative a specific token is compared to the text that belongs to. Cool. So I'll come back. I'll write a structured way because now I've kind of thought it through and I've tried to understand it. I always when I start explaining things when I first learn them, it's very unstructured and it's like muddled essentially. Uh, but over time, when I actually understand it more deeply, I can actually make a structured explanation. So that's what I'm going to strive to do when I come back, by first explaining what self-information is, how it contributes to hard prompt compression, and then talking about the two self-information types, their difference, and then going more deeply into static self-information, specifically with the unigram frequency, and then using that within the self-information score formula to actually determine that score. And then once I do that, then I'll go back and actually understand how to use this score and like what it means at a deeper level. And then we're good to go to the dynamic self-information, which doesn't actually have any really math on its own. It has some like basic like notation here, which is not too hard to understand. I believe this is just function notation. So it's not too bad. Pretty easy work. But yeah, I'll be back. Okay. All right. So, oh, sorry, I forgot to do something. I'll be back. Okay, I'm back. Alright. Alright, so I guess I'll start off by just verifying and making sure um, that I understand static self-information and the difference between that and dynamic self-information, and then we can go from there, right? So let's use that voice agent and do this. Okay, so I've gotten a better understanding of how exactly hard prompt compression works, and specifically there are two different approaches that you can take. The first one is static self-information and the second one is dynamic self-information. Both of them use the concept of basically scoring tokens on how informative they are to their respective text pieces, right? In the case of static self-information, it does not take into account any of the context, so the words surrounding that specific token, or I should say the tokens surrounding that specific token. But the dynamic self-information does take that into consideration by using LMs which have self-attention layers that can actually be context aware. In the case of static self-information, the way that we get the scoring for how informative a token is through first using the unigram frequency, which just takes a target token and loops it over its text body to find how many occurrences of that token happen, and then we divide that by the total amount of tokens to get a proportion, which is essentially how frequent that token is being used. And then based off of that, we derive the static self-information score by using a specific formula, which is I of t, which equals negative log 2 pt. I haven't learned that formula yet, and that is something I'll do later on, so that isn't the biggest of concerns. But basically understanding that we're taking the unigram frequencies that we built and then feeding it into that specific formula to find the static self-attention score. And then dynamic self-attention, so we haven't delved into that literature yet. But basically, to kind of sum it up, the hard prompt compression uses the self-information scores to determine what tokens should be removed from the prompt and therefore debloat the actual prompt being sent to the agent. And it does that through either static self-information, where we're essentially using the unigram frequencies to figure out how frequent a token is being used, and then using that frequency within a formula to determine a score, or through the dynamic self-information, which uses pre-trained LMs to be context aware as to how that token is relevant to that specific text. All right. Awesome. Okay. It should stress test it now. Okay, great. So there is some things that need to be improved, and yeah, that makes sense. Okay, yeah, I thought, oops. Yeah, so yeah, I thought that saying that might have been a little bit risky because I'm not really that aware about dynamic keep saying self attention. I'm not that really aware of dynamic self information, so that's my fault, I guess. But okay, cool. So they do use, I believe, pre-trained LMs, but it's not about relevance. It's about predictability given. Okay. Okay. Again, we don't need to know that because we're still learning that. We're still learning dynamic self-information, so that's fine. Um. Oh. Okay. So this is important because this is a fundamental understanding of hard prompt compression. Okay, before I read what Claude has to say, basically the way that I thought about it is that, and I think I should actually add this here. So I'll say my prior knowledge, my improved knowledge based off of your work. Can you check to see if I have improved my understanding and now am an expert in self-information and how that positively helps hard prompt compression. Okay, I'll just add. Oops, we don't want that. I'll just add a slash and a slash here. Okay, so basically I came with the assumption that the self-information scores are used to figure out how informative a token is within the text body, and then that basically determines what tokens should be removed, because the lower ranking tokens would be the ones that would be completely deleted, since they don't actually meaningfully contribute to the context, or I should say the text, not context. So you can see it automatically fixes all of my errors for me, so that's great. Okay, now let's look at what Claude has said. The self-information scores determine what token should be removed. So that is slightly off. Directionally right, but backwards in emphasis. Okay. So we're sort of the same vibes as saying you're on the right track, but not quite there. The scores determine what tokens should be kept. High score tokens, surprising informative, are preserved. Low score tokens, predictable and redundant, are dropped. Small framing difference, but it matters when you read the algorithms in these papers. They're almost phrased as retained. Okay, I see. So, yeah, so it is the right line of reasoning, but the wrong information, I guess. Okay, I see. So basically, what I thought initially was that it's the fact we take away the low ranking. The way that the self-information mechanism works is that it finds all the low ranking tokens and it removes them, but it's actually the inverse. It finds all the high ranking tokens and it keeps them while removing the low level tokens. So it's just a framing difference, the way that you understand and kind of explain what self-information is. Very, very minor thing, but the way that I have now programmed Claude, it makes sense that it's nitpicked on that specific detail, and that's fine, honestly. Okay, cool. So what I will say to it then, okay, so my line of reasoning was right. These scores are used within the process of removing tokens. However, the self-information scores are specifically used to keep high score tokens. So they retain all the high score tokens, and then through the process of the hard prompt compression, all the other tokens are automatically removed. So essentially, within the perspective of the self-information mechanism, it does not delete the tokens, but rather it keeps all of the tokens which are highly informative based off of the score that it's given. Okay, let's put that prompt in and let's see what it gets. Okay, so just being honest with me. Obviously, I'm not an expert, but I am getting there. Okay, cool. Hold on, I'm just gonna turn off my screen for like 2 minutes. I'm just gonna turn it off for 2 minutes. I just wanna look at some messages which were sent to me. Okay, great. Alright, we are back. Okay, cool. So let's finish this off then by understanding this part of the paper, right? Just understanding how this works. It doesn't really go too in depth with it, which makes sense because it's not actually the unique, meaningful contribution the paper is giving. This is just giving us sort of the underlying, like, I guess, foundation that we need or context that we need to do the paper, to read the paper, because the 3.13 is actually where this paper shines, right? That's what the paper is actually using or proposing. These have already been discussed various times. It's fine. Claude is good. Opus is good with this. Okay. All right. Opus 3. Sorry, wait. Yeah, why the hell is Opus 3 here? Shouldn't that be discontinued? Anyways. So, what I'm going to say is, could you explain what or how this formula works exactly in computing the self-information score for the static self-information process? All right. So P of t is the input, the unigram frequency you already computed. A number between 0 and 1 representing the proportion of the corpus that consists of token t. Okay. Logarithm 2 is the logarithm with the base 2. It answers the question 2 raised to the power of what gives me this number. So log 2, 8 equals 3. I know this is the inverse, right? I understand the mathematics behind it, but why exactly did we use this specific formula to calculate the static self-information score? Is this a mathematical concept which I'm missing, or is there a mathematical concept which I'm missing? And is there something that I need to know when looking at this actual formula to better understand how the self-information, or I should say static self-information process works? All right. Shannon's information theory. The formula is an arbitrary invented for this paper. It's well, yeah, Claude Shannon. That's who this model, this like the platform of Anthropic is named after. The formula is an arbitrary or invented for this paper. It's the foundational definition of information from Claude Shannon's 1948 paper, A Mathematical Theory of Communication. The paper that created the entire field of information theory underpins modern data compression, cryptography, and communication systems. Every time you open a file, stream of video, or connect to the internet, Shannon's work is doing the math underneath. The authors of prompt compression are using his formula off the shelf and not inventing a new one. Is why did these authors pick? Yeah. Why did these authors? Is why did Shannon? So, okay. Actually, the framing that I think would be more relevant to my work is not understanding why Shannon picked this formula or like why it helped him within his research, but rather why did these authors pick this formula specifically from his information theory. And I actually just want to go here, Claude Shannon. Yeah, it's this dude. And his paper is called A Mathematical Theory of Communication. Sorry, hold on. I have to just... Okay, we are back. Okay, so this is basically the paper that is being used in this paper. Oopsie. Great. Okay, so let me just go ahead and send this off and let's see what Claude gives back. What does keep the top K mean? And also, basically, what you're telling me behind the reasoning is that this is just what Claude Shannon has found within his work. Is that when you take the unigram frequency and you put it into the specific formula, you're going to get the self-information score, which is essentially how informative a piece of token is to, or a chunk of text, which is a token in the AI space, compared to a corpus of text. So you keep the top 100 tokens. What exactly do you mean by how surprising a token is in the case of understanding what self-information is? I thought that it would just mean how informative or how important essentially a token is compared to its corpus or the text body that it's from. But if there is nuance to it, what exactly would that nuance be in an easy to understand manner? The reason why the field exists surprise as the intuition prompt is that it explains why rarity equals informative, which is an obvious otherwise. Here's the bridge between the words. It's talking surprising when you didn't expect it. Informative when learning it changes your knowledge. These are two descriptions of the same event. If a token is expected comment, seeing it doesn't change what you thought, so it's neither surprising nor informative. If a token is unexpected rare, seeing it does change what you thought. It's both surprising. Oh, I see. So, informative in the sense of what we were thinking, or what I was kind of thinking, is a little bit flawed because in information theory, what it's basically talking about is when a token is informative or surprising, it's basically when you do not expect it, right? That's when it'll actually provide some sort of meaning into the text, which makes sense, right? Because if a token you expect it to occur in a specific text a lot, it's going to just be redundant. But if a token is surprising, but this is flawed a bit, no? Because if a token is expected, then wouldn't it mean that it's needed within the text? Or is it that the okay, that's a little toughy there. I would like to push back on this idea, because if a word is surprising or unexpected, then it makes sense as to why it's informative because it's adding something to the actual text, right? It's adding an idea or a concept through the strings of words which are unexpected. However, when a token is expected, why exactly would that automatically mean it isn't informative or surprising? It's obviously not surprising, but why is it that it isn't informative and therefore it should be removed? That's what I'm not understanding here. Because there are many, instances of text which are very important in providing some sort of idea, but they're pretty expected. So yeah, I need some understanding or some grounding in what you mean because I still am a little bit rough. So I guess we went from just understanding static self information and dynamic self information to understanding a little bit about number theory as well. Or I should say information number theory. Number, is it information theory? Information theory? Yeah, information theory. And it was literally established by Claude Shannon. So that's pretty sick. But wow, who knew? Just like a little bit of this page, like just this much took me like an hour to dissect, right? Um, Obviously, I'm going at a pace which is really slow because I'm trying to really get to it, crack at it. But still, I do have some maintenance work on the Next Voters website that I'm probably going to want to do as well. So I'm probably going to cut this a little bit short. I'm still going to stay for a little bit more. But okay, cool. Let's just submit this and let's see what pops up. I mean, in the case of Serenity Voilkov, that specific person will be a high surprise to the actual mechanism, self information mechanism. So there shouldn't be a case where one of the names get removed. Hmm. So basically, the static self information piggybacks off of Claude Shannon's work on information theory, where essentially it finds all of the tokens which have a high surprise or a high information, which means essentially that they're rare and not really seen that much, and therefore have a lot to contribute to the prompt. Whereas it will also find all of the low surprising or very expected tokens, and those are automatically removed from the prompt because of the fact that they don't really provide that much information or that much significance, or I should say meaning, to the prompt because they're very easily expected. Again, this sort of line of reasoning I think is there, but I think could be better improved in terms of the articulation and understanding of it because I haven't fully internalized it, if I'm being honest. And the shortcoming of all of this is the fact that it will not understand context because it treats all of the tokens exactly the same, and because of this, even if, for example, there is a token which is a low surprise token or low informative token based off of the mathematical models given in static self information, it might still be highly important in terms of that specific sentence. So it needs to stay, but it doesn't because of the way that we've set up our work. Oh, okay. Fair. That's a fair critique to make. It's based off of the top K cutoff, because there could be very low scoring tokens which are pretty expected that still live within our prompt because of the fact that, again, our compression budget is very generous in terms of what the cutoff is for how many tokens we want to keep in our prompt. That's fair. Okay, fair. So this one is talking more about the actual understanding of like why this is happening, and I shouldn't be conflating the fact that there is a low information token with the fact that it does not provide any meaning, because information in the sense that I'm talking about is basically how rare that token is, right? If it's super rare, then it has a high information because it is a surprising token, which means that theoretically it should be providing us a lot of meaning into our prompt. But that's not obviously that's not always the case, which is what the criticism is. Because if, in the case of having maybe some sort of context, um, a low a scoring token on the surprising scale might be important and needed, right? Ah, okay, I see. So that I guess that's a defense. I've been very critical to this method, but there is a defense to it, which is the fact that a lot of the high expected tokens, which means that they have low information scores, they can be easily reconstructed by the LM with very minimal effort. So that's why we just remove them from the prompt itself. And that makes sense. Like, for example, I didn't need to say and in that case, right? Because we just said that makes sense. In that case, the LM wouldn't even need to reconstruct anything, right? But if I just said something like makes sense, or I don't know. Actually, I don't know. But no, this makes sense though. I see what it's trying to say. Like, okay, actually I do know. Like if I said something like make sentence sentence for poetry, for poetry. If I said something like that, that sounds like broken English, right? This sounds like broken English, but the LM will be able to reconstruct the lower tokens, the lower scoring tokens, which might have been cut, and basically be able to figure out that this means make a sentence for my poetry, right? So those two lower informative tokens were taken out. So basically, just understanding that information in this case is talking about a strict mathematical understanding of information, which is based off of the rarity of a specific text or a specific thing compared to a collection of things. And that's why you can also conflate rarity or surprisingness to information in this case, right? Because this is talking about specifically in the context of information theory. Okay, great. So I think I understand it now better. I'm gonna go through another pass through of just trying to understand everything and making sure that I get it. And once I do, then I'll hop over to dynamic self information. Understand that. I'm not going to be able to do combined scoring and phrase level pruning. I really wanted to get it done, but I actually didn't know that these two were actually part of information theory. Like they were based off of the work from information theory. So I guess I learned something new there. But yeah, so because of that, we went on that whole tangle of understanding information theory and basically the concept of information in a strict mathematical sense, which has been coined by Claude Shannon. So I'll leave this for tomorrow because it does include some math, which I'm probably going to again go into a deep dive like I did today. So yeah, we'll leave that. And again, this is all part of that information theory, which has been theorized by Shannon. So I'm not really gonna understand too deeply into it because I don't need to, right? It's not really relevant to the work that I'm doing because I'm working in applied AI. But still, it's good to know a little bit more about how exactly this sort of works and like where it came from, which was from this paper. Cool. So that was a little bit of a reflection for me. What I'm going to do now is I'm going to take a little break, give my brain a little bit of time to recoup mentally, and then we will finish off static self-information by going through that second pass through, and then maybe a third one if the AI still has some things that I haven't understood properly. And then after that, we'll go ahead and learn about dynamic self-information, and then we'll call it a day. So I'm just going to stop my mic. I just realized my stream was off, was on private, uh, for literally like an hour and 30. I just made it public. That is pretty embarrassing. But it's public now, so hopefully people start showing up. All right. Okay. So I'm going to go through that second pass through and make sure that I understand everything before we move forward. Okay, so essentially, what I needed to understand is that, first of all, static self information is based off of the work of Claude Shannon and specifically the information theory. And essentially, how it works is it understands the information, or I should say the level of information that each token has. And this information is essentially how rare that token is within the list of tokens or the collection of tokens that it's part of. And the more rare it is, the more informative it is. And therefore, it will be kept in the final pruned prompt, right? Now, the way that we actually compute this is by first figuring out the unigram frequency, which is basically just how much that token is used or shown within the text, and then using the unigram frequency within a formula formulated by Claude, not you Claude, but Claude Shannon, to understand to compute the self information score. Then, based off of the compression budget, which is essentially just how many tokens we want to keep in the prompt, all of the low information tokens are removed. Now, this can have good effects and bad effects. The good is the fact that many LMs, when obviously you push this prompt into the LM, they're able to reconstruct the low information tokens because they just see it so often, right? But when you have a low level information token, or a non-informative token, which in the context that it's a part of, which is the surrounding words, it's really important. The static self information is not aware of that, right? So it will actually remove that token even though it might potentially be important. And another obvious advantage to this whole approach is that it's very easy to set up and implement, and also it shouldn't take a lot of computation. Let's go. Okay, so for the first point, thank you for breaking that up. That is actually really important thing to know. So essentially, the token is not compared to the list of tokens, but rather to a specific corpus, right? And that corpus could be anything, but in the case of this paper, it's a large offline corpus which comprises of sources like Wikipedia, ShareGPT, and archive articles. Now, for the second point, that's what I meant. Sorry. I meant that all low information tokens below a specific capped amount are removed. And that is what the top K does. All of the tokens which are above K in terms of the ranking of the informativity, I guess you could say, for the tokens, they will be kept. But everything below that will be removed, regardless of any context, regardless of any external factors, just purely off of the self-information score, which is a fixed score, and it's based off of how rare or how surprising a token is within the corpus of text, not from the text that that specific token belongs to. Great. So that pretty much wraps up everything in terms of the static self information. Now we can move on to understanding dynamic self-information, which shouldn't take too long because really we got a lot of the fundamentals down here. But yeah, so if you were in the last stream, you'd remember, sorry, I just made a connection here, so I thought I would just speak it out. But in the last stream, I talked about how hard prompt pruning or compression essentially uses a scoring system to figure out what tokens should stay and what tokens should be removed. This is that scoring system. The self-information, and one of them, the static self-information, is one of those scoring systems which are used. And we now understand it, and we know that a lot of this work is piggybacking off of the work from Claude Shannon and information theory. Now we will learn about dynamic self-information, which again will look at how informative a token is, which is how rare a token is, but within the constraints of context. So let's see that, basically how that plays out, and hopefully that will give us a round and holistic understanding of the self-information mechanism. Okay. Literally the first 4 words. To capture context-sensitive importance, we query a pre-trained LLM or a lightweight scoring agent at runtime. Given a token T and its preceding context, we obtain the model's probability and compute dynamic self-information. This score reflects the novel information contributed by T in its specific prompt context, complementing the corpus level view. So I'm assuming that it takes the score from the static self-information potentially, and okay, no, it does not do that. I guess that would be something that it would do when you combine it. Maybe I could be wrong. All right, interesting. Okay, so let me actually put this into Claude and let's see what it is able to cook up from it. What exactly does it mean when it's talking about querying an LLM or lightweight scoring agent to give a token and then the preceding context and being able to obtain a model probability? How exactly does that model probability work, and what sort of context is given? Is it bidirectional, like BERT, where context runs from both sides, left and right? Or is it something like the transformers, where it would only be in one direction, which is all the context before it? I'm assuming it would be the latter. Okay, your assumption is correct, and it's the right instinct to have. You've identified the key architectural choice before I even explain it. Let me break it down. Let me break down what's happening here piece by piece. What query an LLM means operationally. When the paper says query a pre-trained LLM or a lightweight scoring agent, it means something very specific and mechanical. Take your prompt, feed it into a language model, Llama, GP2, Mistral 7B, whatever they're using. The model runs a forward pass, and at every token position outputs a probability distribution over its entire vocabulary. Essentially saying, given what I've seen so far, here's how likely each possible next token is. For each position in the prompt, look up the probability the model assigned to the token that actually appeared there. That probability is P underscore model T slash C. That's the entire operation. You're not asking the LLM a question in natural language. You're running the prompt through the model and reading off the internal probability assignments that the model would have used to generate each token if it were producing them themselves. The LLM is being used as a scorer, not a generator. Okay, so that makes sense why it's still a deterministic approach compared to a non-deterministic, because the LLM is not necessarily generating text, but rather it is scoring text because that's what it does under the hood, right? It scores how likely the next token would be, and it builds a probability distribution based off of that. And then it picks a random token to use based off of that. So that makes sense over there. All right. How probabilities compute inside the model? The probability comes from the model's final softmax layer. Every LM ends its forward pass with the layer. Forward pass is moving through the neural networks. So it ends its forward pass with a layer that converts raw scores logits over the vocabulary into a proper probability distribution that sums to 1. For a vocabulary of, say, 50,000 tokens, the model outputs 50,000 probabilities at each position. The probability of the actual token that appeared is just one entry. Okay, so honestly, I'm seeing a lot of work that's being done, which is in the LLM side, or like theoretical LLM, like understanding the actual the actual architecture behind LLMs, which I know, but it is going to take a lot of work in that, to understand how exactly they use or leverage that architecture. So I'm going to keep this for tomorrow as well with this, hopefully, and leave all of this for today. I think we have made pretty good progress, if I'm being honest. Because it is a hard concept, and I'm starting off completely from scratch. But I think I'm good for right now, because I want to focus on some other stuff as well that I have in mind for Next Voters, like maintaining the Next Voters website through Cloud Code. So that's going to be really nice and fun to do, especially after a very mentally draining task like this. But I'll see you tomorrow, hopefully for an hour or two, to continue on with this work. So yeah, that's it from me for now. And yeah. Before I go, actually, I should just say what I learned, and that is just the static self-information. I wasn't into dynamic self-information because I thought it'd be easy, but now that I'm looking at the explanation, it's quite nuanced, or like in-depth, so I'm just going to leave that. But essentially, static self-information works by before we even do that, you need to understand that static self-information uses the information theory. And actually, now that we're at it, sorry, I get a lot of like impulsive thoughts, but one thing that should be made of mention is that if this is the case, then is the self-information score given by a dynamic self-information mechanism representing the same thing that a static self-information system would give? Okay. Okay, cool. I see what you mean. So the scope of to what the surprise is relative to is different from static and dynamic, because static would be to general text, not general English, but the general corpus of which is available. In the case of the paper, that would be sources like Wikipedia, ShareGPT conversation, and archive articles. And that compared to dynamic is different, because dynamic would be how rare is this given the context, which is essentially the tokens which precede the target token. Perfect. So actually, that means that a lot of the work that we did today will lead up to the work, or will be very beneficial to the work that will happen tomorrow within dynamic self-information systems and the combined scoring and phrase level pruning, which we're also going to be looking at. So that's actually really a really good thing to know. Um, Okay, cool. So that means that essentially the self information score itself is the same between static and dynamic. We knew that, but I just wanted to double check that. And it's essentially based off of the Shannon concept of surprise or information, which is just how rare a token is um, within a specific blob of text. And in the case of static, that would be the general corpus, whereas in dynamic it would be based off of context and using the position that it's relative to within that specific pieces of context. Remember, context is just tokens preceding it. So yeah, and again, the concept of surprise within information theory basically is just how rare is this token, and then the more rare it is, the more likely it is to be kept within the prompt and not be pruned out of it. So that's awesome. So learning that base of information theory and how the concept of surprise or information is used within self-information is important in understanding how hard prompt compression removes tokens from the actual prompt for the reduced bloat within the agentic workflow. Awesome. So that is it for me from today. I will probably spend some time tomorrow working on this as well. Um, I guess to finish off, what I will do is I will uh, I'm contemplating it. I was thinking of creating documentation. I'll actually ask it to just create it for me really quickly. Can you create me a documentation which I can add to my code base based off the conversation that we had currently? Do not add anything about dynamic self-information, because I'm actually saving that for tomorrow, because of the fact that it's a quite extensive topic which involves like looking at the internals of an LLM, which I don't want to really do right now. But I am well versed in static self-information, so talk about that in your summary. And also, on top of that, talk about the foundations which were built today, which was understanding how hard prompt compression actually reflects or uses the work of Claude Shannon and what he has done in information theory. Specifically, how self-information scores are just information scores, which is based off of the concept of surprise from Claude Shannon's mathematical paper, A Mathematical Theory of Communication. So understanding all of that is quintessential for static self-information, but also just general understanding of what a self-information does. And obviously, the less rarer a token is, the more likely it is to be removed. But that is dependent on the top K, which is the, I guess you can think about it as the cutoff for how many tokens are being kept in the prompt. The more the more budget you have, the more low level tokens there be. The less budget, the less low level tokens there will be. And then also talk about the problems that we've discussed about static self information, but also the benefits, which is that with static self information, or I guess the viability of static self-information, which is the fact that LMs can often very easily reconstruct low information tokens because they just see it so much in their training data. But an issue with it is also the fact that some information tokens are actually very important for sentences due to their given context, but a static self-information does not understand context. That is something that is reserved for dynamic self-information. Ensure that you have all of these points within that documentation, but it is also short, sweet, and concise. Okay, great. So that should work out for us now very nicely. Okay. While that's cooking up, I have some messages to attend to, so I'm just going to shut off my screen for a bit. Okay, I'm gonna go ahead and turn this back on, and let's see here what Claude has cooked up for us. Okay, great. So this is the surprise formula itself. Awesome. So I was wondering, what exactly is this formula called? It is the surprise formula. Great. That makes sense also. Actually, one thing before I move forward. Before we move forward, just to clarify, the surprise formula is used in both self-information mechanisms, right? It's not only exclusive to static self-information, is what I'm asking. Just to clarify, the surprise formula that Claude Shannon has cooked up is not only exclusive to static self-information, but is something that is used in both static and dynamic self-information mechanisms, right? Okay, great. So both of them, it literally has it has highlighted that or bolded it. So I think we are good to go. Okay, so what I'm going to do now is I'm just going to go to GitHub and go to my profile where I will have the next order is local, and then I'm going to go into my docs here, add file, and then I'm just going to say self underscore information underscore hard prompt pruning dot md, and then I'm just going to add that like that. And actually, I'm actually going to create I'm going to call this compact underscore prompt, and for now I'm just going to put dot init file. I'm going to create a separate thing for it. So I'm just going to delete this. Actually, before I do that, go back to docs. General.md. and delete this. Okay, and then I'm gonna add this here, self underscore information mechanism.md. Great, so I can remove that from here as well. Delete file, and now everything's more organized. Awesome. Okay, and the issue is still about CompactPrompt. So I'm just gonna go ahead and just added documentation related to my work in understanding the end-to-end framework. Done, and we're good to go. So I'll see you guys tomorrow, hopefully. Bye.